Hello guys, once again, Jim Malis. Let's talk about Chapter 11, the problems. I mean, we've already lectured pertaining to these matters. Now let's look at the problems from Chapter 11, or at least some problems from Chapter 11. Problems 25, 43, 57, and 72 from Chapter 11. So let's take a look at 25 and talk about it a bit and then go about trying to solve it. In the Katz book, Volume 1, pertaining to mechanics, problem number 25 in Chapter 11 says the following. A 2.45 kilogram ball is shot into a 0.450 kilogram box that is at rest on a frictionless horizontal table. After the collision, the ball is embedded in the box. So there is kind of an interesting look to this thing. I'll try to draw it a little bit. So it's a 2.45 kilogram ball, and it is shot into a 0.450 kilogram box that is at rest on a frictionless horizontal table. After the collision, the ball is embedded in the box. The box is attached to a 0.30 meter rope, that is attached to the table on the other end. The ball's initial velocity is perpendicular to the rope as shown. If the ball's initial speed before impact is 12.50 meters per second, what is the tension in the rope after the collision? The tension in the rope after the collision is how much force, centripetal force. How much centripetal force has to be exerted by the rope to keep this thing in a circle is what it is. Well, the tension in the rope is that amount of centripetal force. So let's take a look at that. Let's draw something and see what we can say about it. We'll kind of take it from there. Sorry about that, guys. I'm kind of juggling the chalk a little bit, find out the best chalk to make this legible and at the same time keep the board kind of looking halfway decently, I guess. I guess, look, we can probably look at it a bunch of ways. Let's take a bird's eye view on this because I'm not going to be able to draw as good as the artist drew in the book. But if you look at the book, I mean, this is the center. There's a pole coming right out at you. This is the box. And this is the ball being shot right at it. The ball and the box are going to be united pretty much at that point. And, and then basically we're talking about circular motion. So they're asking a bunch of stuff here. They are looking at this being 0.30 meters right here. The ball being 2.45 kilograms, the box being 0.45 kilograms. Initially, the ball is coming right at the box before the collision of 13.5 meters per second. Let me just make sure we got that. Yeah, 13.5 meters per second. That's before the impact. That's the ball's initial speed before impact. It's 13.5 meters per second. What is the tension of the rope after the collision? All right, guys, I drew enough arrows here. Who knows, that might be more confusing than helpful. But anyway, you can see here, they're talking about, you're talking about the box right here. There's the rope. There's this guy firing that way. And it's going there. Maybe provide a little bit more contrast and just get an idea what's happening there, guys. How we're gonna be doing this. All right, that's a simple, and that's a bird's eye view of what's going on. How are we gonna take it? Well, we talk about momentum. We talk about momentum a lot, and we talk about momentum being conserved always. So if that's the case, PI vector equals PF vector. I will call the more massive object capital M, the less massive object. The less massive object is the box. The more massive object is the ball. So, kind of like need to emphasize that one's more massive than the other, I guess you could say. Mass of the ball, initial velocity of the ball, plus mass of the box not moving. Together, large mass, small mass, and it's going to take off at V. Let's see what we can say here. Well, yeah, I mean, there's a good amount we can say here. We know that's true. We also know that the tension is going to be the centripetal force. The tension is equal to the centripetal force. That's going to be the total mass of the system times the velocity of that system squared over R. And I think they might have, whatever, capital, small, whatever. I'll kind of keep it consistent with my notes. Not going to make a big deal out of that one, guys, but this is important. That's the tension. It's going to be equal to the centripetal force. So what we have here, well, we can say a lot of stuff. I mean, I'll tell you what. Let's kind of get ourselves out of the woods here a little bit and see how we can say a couple things, I guess. Let me solve for the generic V here, because that's the VF, the V after the fact. Divide by the quantity, capital M plus small m on each side. M times 0 is just 0, so let's not make a big deal out of that. This right here implies, all that right there implies that V is going to be equal to capital M over the quantity capital M plus small m times VI. So there's a lot going on here. I'm staying more explicit. I'm staying with the symbolism a little bit more, maybe a little bit more than I need to. For sure more than I need to, but I think it's good to look at things more or less abstractly. If you can solve things with non-numeric symbolism, then when you put the numbers in there, it's very easy. So we've got this. What does that mean? Well, that means wherever you see this, put that right here. The tension is going to equal this over R. V is V. Square the V. Square, I'm sorry, everything had to be squared there. So capital M squared, the quantity capital M plus small m squared, and V sub I squared. Everybody squared. All right, well, there it is. Capital M, the quantity capital M plus small m, and the capital and the quantity capital M plus small m here, that cancels, just leaving one of them here. The tension is going to be, it's going to be m squared over m plus m, because there was a cancellation there. There's R here, and there's VI squared. I mean, there's written a number of ways. That's essentially the way I wrote it, a little bit differently, not much. The rest, guys, plug in the numbers. Plug in the numbers. Capital M is 2.45. Capital M is 2.45, square 2.45. VI is 13.5, square that. So 2.45 squared, 13.5 squared, divided by the product of the sum of big M and small m, which is 2.45 plus 0.45, which is 2.9. 2.9 right here. And capital R right here is 0.3. Plug all the numbers in there, guys, and grind the whole thing out. And again, the numbers are in there like we already said. And if you just walk it through there, like I said, this is going to be, capital M is 2.45 squared. 2.45 squared. VI is 13.5. And you're going to be squaring it. This and this is, as we said, 2.45 plus 0.45. It's 2.9. R is 0.3. The rest is arithmetic. The rest is just plain out math. The tension is 1257. $1,257.4 newtons. So there it is. There it is. Let's go to 43. Now there's a lot there. I mean, this is a rough one. I mean, this can be a little rough. So let's kind of be careful with it. We'll play all the games we got to play with it and see what we're going to say about it. You read it out to you, and then we'll take it from there. Problem number 43. There are two pendulum bobs. Pendulum bob 1 has mass M1 on it. It is displaced to a height h1 and released. Pendulum bob 1 elastically collides with pendulum bob 2. That means kinetic energy is conserved, you guys, of mass M2. A and B, find the expression for the maximum height h2 of pendulum bob 2. If M2 is 2.5 M1, h1 is 5.46 meters, what is h2? So some really, really interesting old school type problem there. So let's take a look at it and see what we can say about it. Now for problem number 43, you guys, they're talking about an elastic collision. An elastic collision means a perfectly elastic collision. Kinetic energy is going to be conserved. That's true, but you really got to be careful how we play this. What we label what and how we label it. So let's take a look here. So we got 25 under control. Let's do 43. They are basically saying there is a lot here. How exactly we're going to pull it off, we'll see how we're going to pull it off, but it should go rather well once we do a lot. So for 43, there's two pendulums. There's going to be elastic collisions. When this collision happens, it's going to be an elastic collision. So momentum is always conserved no matter what kind of collision you have. But kinetic energy is conserved only in a perfectly elastic collision, or they call it an elastic collision oftentimes. So, you know, you got ceiling right there, I guess you could say. This guy, well, if I say anything about this guy, that guy, first of all, this is not going to be a good drawing because I'm the guy drawing it. That's one thing for sure. But this is M1, and it's going to come right down. It's going to hit M2. So this is, you got to be, see exactly how they want to do this, I guess. It's going to hit M2. So this is this guy coming down, and he hits. This is M1 hitting him. M1 hits him. And then this guy climbs up, and we don't really know how high he climbed up. We'd have to look at it. I mean, I don't want to make any definitive statements here, but it's going to climb up to here, and this is still M2, and this is still M1 right here. Well, the initial height of all this business was H1. That's H1. The height after the collision, that's H2. It looks like they're the same height, but that's not guaranteed. This is just a drawing, guys. It's not a guide. It's just a drawing. So here's H2. Here's H1. This guy gets released. It comes down, and then let the show begin. They're probably going to keep colliding. Boom, boom, boom. They're going to keep hitting each other. If there's no dissipation due to friction, they keep hitting. Colliding, bouncing off, colliding, bouncing off. We can discuss that some other time, depending on what problem warrants us to discuss something like that. Right now, we only care that there's one collision that we care about. That's the first collision. Bam, they hit, something happens. The situation is, see, they don't say a lot here. They don't collides elastically with pendulum bob 2 of mass M2. One of them ain't moving. M2 was initially not moving. They didn't really tell us that, but I guess, they always talk about Occam's razor, you guys, right? You always talk about you got to go for the easiest assumption that's present when you're going to do something like this, and then from there you take it and you see what you can do. So there's, as we said, I mean, there's the H1 right here, right? And there's the H2 right here. Okay? How that whole thing's going to play out, and that's how we're going to go about it. Well, having said that, they want to know what the height H2 is going to be. There's an easy way and a hard way. Either way, easy way or hard way, it's pretty easy, but it's kind of tedious, but that's part of the game sometimes. It's got to get a little tedious for us. Remember, whenever we have perfectly elastic collisions, or as they call it, simply an elastic collision, kinetic energy is going to be conserved. Momentum is conserved. It's a vector quantity. They're in line with one another, so I'm not going to, the negative and positive will work just fine on this. If this is indeed the case, let me try to, I have this worked out in more excruciating detail in your notes in Canvas. So here it is for you. It's in your notes in Canvas. Go for it. Take a look at it. I do not, let me think here. Just trying to think here really quickly. Yeah, I don't want to rederive what I've already done. We already had, when we talked about collisions, I already said what happens if this, but I didn't want to rederive what I already had done, but I do have it rederived here in problem number 43 for you in the notes in Canvas. So you can look at it, you can see it again, it's good practice. But you saw me play the game right here. You saw me play that game right there. When two things collide and they are more or less in line with these, doesn't sound like these guys are in line with each other, but when they first collide, they're on the same line. And then after they bounce off each other, they're instantaneously when they first collide, they're on the same line. And instantaneously when they bounce off each other, they're still on the same line. So the conclusion I drew last time was You do all the song and dance that I showed you in the notes pertaining to collisions and conservation of momentum and all that stuff that I've already shown you in the notes. Use that derivation. And what does that derivation say? Well, it says, at the end of the day, at the end of that whole song and dance, there's a V1I and there's a V1F. And if you add the two, it's the same as V2I. Or how did they write it? They wrote V2F plus V2I. It doesn't matter who you write first. Look, the sum of the initial and final velocities of the first object equals the sum of the initial and final velocities of the second object. Yeah, we derived that. Somewhat of a lengthy derivation, but it wasn't too bad. We derived it. You already have that in your notes. So let's just jump to the chase. I do have it worked out for you again, though, on Canvas. So you can look at it once again on Canvas when you look at it, when we're doing this. All right, so when you do this, this holds for perfectly elastic collisions. For elastic collisions, now let's proceed with the problem, you guys. When they hit, now we got to be careful. All of these are just before and just after impact. These guys, this guy right here, the V, you got to be careful. I know what we have said in the past, and we all know that. Now we got to be careful. You know that initially when you're holding mass M1 up here, it ain't moving. Yeah, I don't want to call V1I equal to 0 up here. I know that it is. I'm going to call V1I for this guy. I'm going to call it V1I right here, right before it impacts. I don't care about it up here. That's trivial. That's 0. I care right here. Same way I don't care about it up here. Why don't I care about it up there? Up here, the V2F, I don't even want to call it V2F. There's a final velocity for mass 2 up here, which is equal to 0. And there's an initial velocity for mass 1 up here, which is also equal to 0. It's 0 up here, and it's 0 over there. I don't care about that. I care just before impact, and I care just after impact. Not way, way up there, when I know everybody's at 0 way, way up there. Way, way up there, this guy ain't moving. I get that. Neither is this guy. At the end of the whole thing, this guy up here ain't moving. I get that too. I care right about just before and right about just after. Well, right about just before, this V1I is going to be how fast is that one going right there? How fast is that guy going right when he swings down? Okay, I have to find that one out. This guy initially, and again, we started, like I said, we had V1. Let me write this enough times here, guys, so we can kind of. Yeah, we know that. V2I initially on the bottom, this guy right here, yeah, he ain't moving. That one, I'm going to have to concede that, which makes it easy. He ain't moving. V2F is right when he gets hit. I want to know what happens right when he gets hit. That's going to be the V2F for that guy, right when he gets hit. Here he's 0, the V1I, it's not really... mass 1 up here is 0. Mass 1 up here is 0. Mass 1 right here is something. Tell you what I'm going to do. Let's use energy considerations, ladies and gentlemen. If this guy falls H1, MGH is the potential energy up here. M1GH1 is the potential energy up here. All that potential energy is going to become kinetic energy right here. It's going to become kinetic energy right there. It's going to be M1GH1 is going to become kinetic energy right here. So let's see exactly how they want to say this, how we want to say this. just trying to argue this. We know, we already took care, this is important stuff. Let's talk about that. Yeah, sounds good to me. Right before impact, the mass is going V1I at the bottom, right at the bottom before impact. M2 has V2I right before impact. Well, we said V2I was 0. It ain't moving. Initially, nobody's moving, but when this guy comes down, this guy's stationary, and right here he did pick up speed. We'll call that speed V1I right here. And then bam, the other guy takes off. So M1 V1I equals what? Well, that's the only guy there, man. I mean, it was the other guy was M2 V2I, and we said initially that ain't moving. It ain't moving, that's 0. Then the other guy bounces off. He might go forward, he might keep going forward, and he might fly backwards. We don't know, but it's a vector quantity. That's V1F. We got to talk about that. And the other guy is M2 V2F. We have got M1 V1I. M1 V1I equals M1 V1F plus M2 V2F. I don't care about way up top. Way up top over here at 0, way up top over here at 0. That's trivial. I care right before impact and right after impact. There's a lot going on here. Let's talk. Let's talk a little bit, I guess. Then you say the kinetic energy is preserved. What does that mean? That means 1/2 M1 V1I right before impact V1I. That's all kinetic energy. The other guy doesn't have kinetic energy because he ain't moving. Then right afterwards there's kinetic energy. Yeah, that's true. True. Yeah, you remember some other stuff here? Do you remember all of that potential energy equals the kinetic energy right down here? Because all of the potential energy became kinetic energy. All of this potential energy, M2GH2, was acquired from all of the kinetic energy after the collision. So there's something we can say, guys. We can say that M1GH1, for whatever it might do for us, M1GH1 is 1/2 Yeah, right before M1 punches the stationary M2 with this much kinetic energy, right before that happens, that's how much kinetic energy it has. Where'd it get all that kinetic energy? From the fall. The rise to this height and this level of potential energy arose from a kinetic energy equal to this. All this right here came from here. And all this right here came from there. All the kinetic energy brought it to the height of here, and potentially all the kinetic energy gave it that much potential energy, and all the potential energy, when it got released, created that much kinetic energy. Well, I think this is going to help us when we come over here. I mean, I guess I don't want to be too simplistic on the whole matter, guys. Once you got all this in mind, it's done. It's the hardest part of the problem. The rest is just sitting down and patiently doing the problem and not making a careless mistake. So that's it. Well, I got it all. I'm looking at it. It's whatever it is. Let me see. You know, there's a whole lot. I mean, I don't know that we need to go there, but we could say some other things. What are we going to do? We could tinker with this stuff a little bit. Maybe helpful, maybe not. Potentially. Let's see. I'm looking at this thing. If push came to shove, if I wanted to find V1I, if I wanted to find what V1I was, and if I wanted to find what V2F was, I solve for V1I in this equation. I solve for V2F in this equation. When you do that, you draw the conclusion V1I equals, let's have a look at it. I guess here's how you do it. You multiply by 2 on each side and divide by M1. That's 2GH1. Let's try it again. Let's multiply by 2 on each side and divide by M1. That's just 2GH1 equals VI squared. You get the square root of each side. And that's just the square root of, that looks similar to a lot of the math we've done in the past. In similar fashion, you will also do the same kind of logic, and you get 2GH, the square root of 2GH2. So V2F equals the square root of the product, 2GH2, and V2 and V1I equals the square root of the product, 2GH1. Okay, got a feeling we needed to do that. I don't think there's not really much. I don't think there's much optional on that one. We gotta have this data in front of us. I think it's going to help us tremendously when we do it. So when we look at this, let's look at it. We've got a lot of information. We may or may not need all of it, but we got a lot of information, guys. It looks pretty good to me. Well, we try to give some kind of look at this thing that makes a little bit of sense. We gotta somehow make sense out of this thing, and the way, so we use the aforementioned equations just mentioned in here, and see what we can say here. Now, for some reason, I'm just arguing with myself here regarding how I want to proceed with some of this stuff to get here. I think we need a lot of the data that we have. So I don't think we're going to get out of this thing looking too good. We got to say we know all this, and we got that. We're going to use this. We've got these right here, and this is very key. This is very much a key. What we need to be doing here. This is very important. So that stuff we got to, we'll look at that. We know these, so let's not, two different dynamics here. We got this thing right here, not the same as that over there. Okay. So right here as we got it. So I'm just arguing with myself how you can look at this thing, because I'm not, again, guys, let me forgive the attempt at artwork here. That's the crux of the whole thing, guys. If you got this under control, and you know these right here, because they came from that. All that encased in green and this encased in green, I think that's all you need. Gets a little confusing because it's confusing what's getting asked sometimes at some level, guys. Let's kind of look at it and see what we can say about it. Well, I'm not entirely thrilled how I did this, but let's keep a couple things in our mind, I guess you could say. I guess to make this thing work, we got to somehow solve for somebody. We can find out what he is. V1F is where it's going to go, and I don't know, there's a whole bunch I did. I wasn't entirely thrilled by this whole, look, if this thing right here is 0, and you got V2F is equal to all this, you can write a whole bunch of stuff here. You can write V2F right after the collision. How fast is mass 2 going right after the collision? That's V2F. Equals V1I plus, let's see here, right. V2F equals V1I plus V1F. Right. And then from there, you can kind of solve for V1F. I don't know, it's kind of like a horse apiece, you guys, but let's just have this. I'm trying to go with some of the data I did generate. You can write it like this. You can write it like that. There's yet another way you can write it. We don't care too much now, but got a feeling we can see a couple things here. What we did was we said, okay, can we make some sense out of this? Do you guys remember we had 1/2 M1 V1I squared equals 1/2 M1 V1F squared equals 1/2 M2 V2F squared. Maybe that's why they went here. They wrote it like this. Let me see here, guys. I was debating some of the stuff here, how I want to write it. Can we talk? What's 1/2 M1 V1I squared? One half M1 V1I squared is M1 GH1. That's 1/2 M1 V1I squared. 1/2 M1 V1I squared is M1 GH1. The second one, V1F, is equal to V2F V1I. So let's write it here. V2F V1I, that's V1F. That's this guy, V1F squared. One half M2. Well, hold the phone. I mean, let's make it easy. What is that last term? What's the significance of that last term? It is right up here, guys, right up here. 1/2 M2 V2F squared. 1/2 M2 V2F squared. That's M2 GH2. I had to have GH2 somewhere. I'm being asked to solve for H2. Doesn't help not to have H2 anywhere present if they're asking you to solve for H2. We got to know that. a little bit of an instinct when we do this stuff, guys, how we're going to go about it. Wow, that's crazy. Well, okay. Let's see what we can do. M1G H1 equals, this thing goes, and it goes 1/2 H1 V2F squared minus 2 V2F V1I plus V1I squared. Plus M2 GH2. Interesting. Yeah, it's kind of all over the place on this one. Yeah, there's a lot here. M1GH1 M1GH1 1/2 M1 V2F squared. It's a little odd. It doesn't. We'll see what the significance of that is. Bring the half in here. You got minus M1 V2F V1I. We got 1/2 M1 V1I squared. It's the only one that kind of resembled something reasonable, I guess you could say, for lack of a better word, at least something we've seen before. In fact, I'd like to circle that. 1/2 M1 V1I squared. 1/2 M1 V1I squared is M1 GH1. This right here is equal to M1 GH1. There's a lot going on here, guys. Let me try to cut to the chase a little bit. 1/2 M1 V1I squared is M1 GH1. If this whole song and dance is M1 GH1, and this one's M1 GH1, let's subtract M1 GH1 on each side. This is the same thing. They're equal. So we got that. Okay, I don't want to erase any of it. You know that. I've got a lot of blackboard space. I'd have even a lot more if we were all together. If it's a big enough room, there's even more space. But it is what it is, guys. So I gotta move a little bit. I gotta erase a little bit when we're doing this. Okay. Remember, the 1/2 M1 GH1 is 1/2 M1 V1I squared. Plus here, not a half here. Sorry about that. M1 GH1 equals 1/2 M1 V1I squared. 1/2 M1 V1I squared equals M1 GH1. That's equal to that, which is equal to this. So cross him out and cross him out. Subtract M1 GH1. Subtract M1 GH1 on each side. This goes, and this goes. Then we got this. All set equal to, set equal to 0. All this set equal to 0. What does that mean? It means we're here. Yeah, it's true. If it's true, try to tinker with it a little bit then. Well, if it's set equal to 0, why don't you take this guy, M2GH2, one of the most important elements of this thing, and I managed to block it off. M2GH2, I hope that's a little more clear to you guys. It was being added. M2GH2, leave that alone and get all these other guys over to the other side. Add a positive M1V2F V1I on each side, and add a negative 1/2 M1 V2F squared on each side, and just leave this guy to stay, M2GH2. What happens is we get M2GH2 equals M1 V2F, a little odd looking situation there, but there it is. One half M1 V2F squared. Yeah, I didn't say it looked that great, but you're looking at it like this. That's when you isolate the M2GH2. Isolate the M2GH2 and you get this. We are remembering, of course, and of course I'm sure I erased it somewhere. I think I did, but let's just write it down again. Now we can use V1I equals the square root of 2GH1. We can use V2F equals the square root of 2GH2. I put them in there. Let's see. Maybe this is going to make things look a little more reasonable for us. We'll take a look at it, I guess. We got M2 GH2. We've got M1 right here. V2F is this guy, the square root of the product, 2GH2. V1I is this guy, the square root of the product, 2GH1. When you multiply two square roots together, we got M1. We've got, we got V2F, which is 2GH2. And the other one is 2GH1. So V1I is 2GH1, V2F is 2GH2. V2F is 2GH2, V1I is 2GH1, the square root of 2GH1, minus 1/2 M1 times V2F squared. V2F squared is the square root of 2GH2, the square root of the product 2GH2 squared. Okay. It's a bit of a mess all the way around. But something, at least we know something. Looking at this thing and trying to figure out some good ways to talk about it. Let's see what we can say here. Why don't you take this guy right here and square it? Square the square root and get 2GH2. 2GH2 times 1/2 is just, 2GH, the square root of the product, 2GH2 squared is 2GH2, times 1/2 is just GH2, times M1, M1 GH2. A little odd, but it's the reality. The other one, it's a little easier than you might think it is. The product of two square roots is the square root of the product. You can put them both underneath one root. The product of two roots is the root of the product. You can put this underneath, and you can do it another way too. This is square root of 2, that's square root of 2. It becomes 2. This is square root of G, this is square root of G. It becomes G. Then it's just square root of H2 times square root of H1. So what happens is you end up getting, for this one right here, you end up getting M1. Let's just see. Okay, M1 the G is the G, the 2 is the 2, and you got square root of H1, square root of H2. The square root of 2 times the square root of 2 is 2. The square root of G times the square root of G is G. The square root of H2 times the square root of H1 is the square root of H1 times the square root of H2, or the square root of H2 times the square root of H1. Not a big deal. That's equal to M2G H2. Yes, I wonder why I pick problems that take 9 hours to solve as well. But anyway, I think it's worthwhile. I think it's definitely worthwhile for us, guys. Yeah, we know the deal. I mean, we're already here. Maybe there's something we can do here. Maybe there's something we can get out of this whole thing to get us out of the woods on this thing. Man, there's a lot of stuff that comes to mind here. Let me just look at it. I think it's okay. Ain't really that obvious what it could be, but let's see what we do have. We got all that. M1GH2, add M1GH2, add M1GH2 on each side, and after you add it to each side, let's see what I've done. Let's just see what conclusions we can draw, you guys, when we do that. Again, getting the equations is really the heart of the whole matter, but you got to be careful. You got to keep your composure, and you got to get this thing done. Just got to get it done. Let me add M1 right here, down here. Let me add M1GH2 on each side, and let's see what the mathematics tells us. M1GH2, M2, M1GH2 plus M2GH2. The hardest part, guys, is not making a careless mistake like I'm about to make when I'm not paying attention. So you add a positive M1GH2 on each side, and you get M1GH2 plus M2GH2 as well equals 2 M1G, and then the square root business, equals 2 M1G, and then the square root business here. You got this. All right, it's basically all over the place, but I think we can do it. I think we can do it. We got what we got here, guys. We have what we have here. What do you say? You pull an H2 out of here. Okay, that looks pretty good. Still not saying we're saying a lot, but we're saying something. Sounds good to me so far. Now, is there any way out of the woods here, man? We're trying to solve for H2. Presumably, we know what M1 is. We know what G is. We know what M2 is. We may know H1. We certainly don't know H2. Can we do something here? It depends. It depends what assumptions we're making. It depends what assumptions it is that we're making, you guys. We try to think of something here. This is easier than you think, actually, guys. This is actually easier than you think. Why don't you divide by the square root of H2 on each side? Let's do a couple things, actually. Let's divide by the square root of H2 on each side and divide by the quantity M1G plus M2G on each side. And we end up getting this. We end up getting 2 M1G square root of H1, that stayed, over this right here. M1G plus M2G. I can go faster, guys. I just don't like going faster sometimes. It's more convenient to go faster. Sometimes I do have to go faster, but oftentimes I'd rather not. I just kind of, let's kind of look at this and see if there's something here that can kind of, you're about to get out of the woods pretty well right here, guys. What happens is you got H2 over the square root of H1. I'm sorry, H2 over the square root of H2. H2 over the square root of H2. This right here is, how do you want to do this? I mean, you could say M1G square root of H1. M1G square root of H1. Pull a G out of here, guys. G times the quantity M1 plus M2. Well, in an odd way, this is looking a lot better. The G's cancel. The G's cancel. And again, guys, I hate to, at some point I got to erase more things than I want to erase, actually, but let's see what we got. Looking good to me. It's looking all right, guys. What do we got here? We did the whole song and dance there. We got to here. We got to here. We got that out of there. We got that's H2. 2M1 square root of H1 over M1 plus M2. Two M1 square root of H1 over the quantity M1 plus M2. Wait a minute. Isn't this thing right here, H2, the same as the square root of, isn't H2 the same as the square root of H2 squared, which is the square root of H2 times the square root of H2. Well, what's the square root of H2 times the square root of H2 divided by the square root of H2? Put it another way. How many times does the square root of H2, how many times does the square root of H2 go into H2? Goes in the square root of H2 times. Square root of H2 equals. Okay, now we are somewhere. We're assuming we knew from what height this thing's getting dropped. And now we're in business, I think, ladies and gentlemen. What do you say? If two things are equal, do they remain equal if you square each side? Yeah, I think that's reasonable. If you take the square root of H2 and square it, and you take all this and square it, you have got you have got H2 is equal to, well, square the 2, you get 4. Square the M1, you get M1 squared. Square the square root of H1, and you get H1. Square all this, square the sum of this, go ahead and do so. And you're done. And you're done. Yeah, that's out of control, guys. I'm not sure how, not sure of a good way to do this without it driving us nuts. And, well, as you saw, it just did. This is it. This is an abstract way of doing this with non-explicit numeric symbolism. With non-explicit numeric symbolism, you can plug in any symbols you want. As long as you're just missing one item, you can solve for anything. With the way we got this set up right now, guys, if I don't know, it'd be pretty tough. There's ways. Look, how many unknowns are there right here? H2, H1, that's 2 of them. M1, M2. There's 4 unknowns. If I know any 3 of those 4 unknowns, I can solve for the 4th one, whichever one it may happen to be. Anyway, that's big. That's big time important. That's 43A. 43B, well, after you did all that hard work, guys, it should be easy. If they're going to say to you, well, it's debatable how easy it is. This is the thing that's going to get us to where we got to go. It's as simple as that. What does that mean? It means you already know this. We did a lot of work to know this, so we know it. Did a lot of work to know this stuff. We know that M1 equals M1. We know that M2, they told us. Now, hey, guys, suppose M1 equals M1. We always know that. Suppose the second mass is double plus 0.5. It's 2.5 M1. Let's say they told you that. They gave you this for this guy. You already know this guy. They gave you this for the M2. The M2 is 2.5 M1. They told you H1 was 5.45. Forgive me. They said it was 5.46. That's it. Sounds good to me. Let's find it. They didn't tell us what M1 was explicitly, so we better be careful. But I think we're going to be okay. 4, if we're careful, I think we're okay. 4 M1 squared, H1, over M1. Well, he already told us what M1 was. This guy right here, M2, is 2.5 M1. Then we're going to square it. Well, let's keep going. This is 4 M1 squared, H1. This is 1 M1. This is 2.5 M1. This is 3.5 M1 squared. Okay. See what else we got. H2. This is 4. This is M1 squared. This is H1. 3.5 squared is, it's going to be, there's a lot of ways to do this. It should be 12.25. Let me just kind of think about it a little bit. The 0.25 we can kind of think about. 1.5, 1.53. Yeah, it's 12.25. It's 12.25 M1 squared. What's going on here? Yeah, good. I'm glad they didn't give me a specific number for M1 because I couldn't do it. But they gave me a relationship, the proportions, the measuring sticks. If it's a ratio, I can probably get out of the woods. And I did. And we did. So we're right there. What do we got? We got H2 equals 4 over 12.25 times H1. Yeah, that's interesting. Again, we got the calculators, we got everything that we need. We're going to plug in what we need. H1 is 5.46 times the ratio 4 over 12.25. 4 over 12.25 times 5.46 is going to give me H2. H2, not going to be too big. Well, yeah, the thing was pretty massive. The height ain't going to, why is the height not going to be that high? Well, I'm thinking one thing that kind of that comes to mind is if it's 2.5 times more massive, probably ain't going to go as high. I could, again, never say never, never say always, but this should not be too surprising as a conclusion. Sorry, guys, for the long dance on this one, but here it is. There's your answer. H2 is going to be 1.7. H2 is going to be 1.78 meters. That's 43. Stuff's not too bad, but it'll make you think. It'll make you think a little bit. All right. 57 and then 72. So let's see here. Let's get the setup here. $57. Let's see what they're saying there. All right, they try to make this a little bit interesting for us. So let's talk a little bit. $57, again, chapter 11, of course. 57, a bomb explodes into 3 pieces, A, B, and C, of equal mass. Piece A flies with a speed of 40 meters per second, and piece B with a speed of 30 meters per second, at an angle of 90 degrees relative to the direction of A, as shown in the figure. Determine the speed of piece C, and the direction of its velocity relative to the direction of piece A. Okay. Let's talk. Shouldn't be too bad. It shouldn't be too bad at all. Let me just, but caution's needed. We can kind of give this number of looks here. How they want the answer given. Just watch out for how they want the answer given, guys. That's the thing where we really got to pay close attention to it, I guess. Let's see what we can say. Okay, for 57, see what we can say here. The way they brought the thing up here, let's how they want to talk. Let's speak their language, I guess you could say. The masses are equal. This guy's going off this way. That's B. And that's 30 meters per second. The other guy's going off this way. And that's A. Is that? Well, we know momentum's conserved. The bomb was just there. It wasn't really moving. Look, there's a lot you can say here, but we're going to assume the bomb was stationary somehow, floating or hanging from a tree. And here's this experiment that's taking place to see what conservation of momentum is all about. Initially, there's no momentum at all. After the explosion, the vector sum of all the momenta, is going to be 0. Momentum final, all the vector sums are going to add up to 0 because initially there was no movement of the entire bomb. Movement of the entire bomb had mass 3m. Each piece is mass m. M, and m. Add m plus m plus m, that's 3m. Whatever, there's a lot of ways you can talk about it. The big thing here is, this is just a guide, guys. This is just a guide. Here's C. This is some vector, V vector. I can figure out how big this thing is and everything else. This is how they're measuring. Why are they measuring that way? Don't ask me. But that's part of the game. That's part of the challenge they're giving you. That's the way they're measuring. From the vertical going counterclockwise. That's the theta they're talking about. Going like that. All right. Without further ado, let's just kind of talk about this thing. Let's figure it out. We'll call each mass M. M is the mass of each one of them. What does that mean? M is the mass of particle A. M is the mass of object A. It's also the mass of object B. It's also the mass of object C. All the masses are equal. We know that the initial momentum, or at least we're assuming that, the initial momentum equals the final momentum. We know that, and that's the 0 vector. We know that after, because initially it ain't moving. Afterwards, everybody's moving, but everybody's moving in a contradictory manner, if you'll allow me to say. They're moving all over the place. But they're all going to cancel each other out. 0 vector is MA VA vector plus MB VB vector. Here the vector stuff is real important because everybody's flying everywhere and it's a vector sum to get these under control. 0 vector's looking like that. Yeah, we already said MA was M, MB is M, MC is M. Pull an M out of there, guy. If I pull an MA out of there, it's the same as pulling an MB out of there or an MC. MA, MB, MC are all equal to M. Just pull that out of there. Divide by M on each side. VA vector. VB vector. VC vector. All the vectors add up to 0, you guys, and I kind of went into that however you want to do it. Now, what does that mean? If all the vectors add up to 0, all the x components got to add up to 0, and all the y components got to add up to 0. If you break these up any way you want to break them, but you know what? At the end of the day, these guys come out to the 0 vector, and it doesn't matter what coordinate system you use. When you're doing this, you're gonna, that's something we gotta watch out for. So let's see what we got here. So we got it to here. What does that mean? That means the summation of all the x's got to be equal to 0. So what does that mean? That means VAX plus VBX plus VCX got to equal 0. Okay. Notice, ladies and gentlemen, that VA vector goes straight up vertically. There is no horizontal component for VA vector. It's all vertical component. So VAX is 0. VBX, this one for the VA vector is all vertical component, no horizontal component whatsoever. The VA vector is all vertical component and no horizontal component whatsoever. The VB vector is all horizontal component and no vertical component. It might make things easier for us in a lot of ways. So we're looking at it. VB vector goes 30 to the right. That's going to be plus 30. Now I got to really concern myself with signs, you guys. The C, man, you got me on that one. That's theta. So now you got to watch it. Now we got to be careful. VCX is something. Yeah. VCX is negative 30 meters per second. It's got to be. He's got to cancel out with the other guy. You just saw it. Sounds good to me. Now, let's talk about the other guys. VAY plus VBY plus VCY got to equal 0. VAY, well here, yeah, this does have that does have a vertical component. It's 40. VBY, yeah, this does not have a vertical component. One of them's all horizontal, the other one's all vertical. All vertical has no, that's the A guy. The A guy is all vertical, no horizontal component. We already said that. The B guy is all horizontal, no vertical component. Don't know what VCY is, but that's almost going to be trivial. 40 plus VCY equals 0. Add a negative 40 on each side. VCY yeah, true. Definitely true. The rest is a cakewalk. Yeah, there's a negative, there's a negative 40 right here. Negative 40 right there. And a negative 30. Again, this is a bad drawing on my part, but it's a negative 30 right here. So it's negative 30 right here, negative 40 right there. So that's where the components are when we're dealing with this thing. So we just got to find out what this guy is, and that's the Pythagorean theorem. There's a lot going on here. Now, they want you to report it their way. You've got, this is, ladies and gentlemen, VC in totality. That's VCY, which is negative 40. I'll tell you what, in terms of absolute value, VCY is negative 40. What do you guys say I just call it 40? And this guy right here, I know it's negative 30. What do you say I just call it 30? Got this, I got this, and I got this guy to find. The VCY. Okay? So you're looking at, can you find the VCY here? Forgive me, just the VC. V sub C. Doesn't look like a subscript, but that's a subscript. V sub C. Okay? The rest is kind of a joke. The rest should be pretty straightforward, you guys. You can write another angle right here. You can call it phi if you want. You call it phi, and this guy right here is the theta that you're talking about. I know that if this is phi and this is theta, theta plus phi equals 180 degrees. If they said find it here, find it there, who cares? They asked for theta. Let's play their game. I don't know what to tell you. I mean, I could tell. Actually, I do know what to tell you. I think it's pretty straightforward in the regard of how they might want to ask this thing. Look at my notes. They're pretty consistent with what I'm doing right here, guys. All of this is in the notes. Everything I do is, for the most part, I mean, on occasion maybe not, but for the most part, it should be in the notes. Like 95 to 99% of what I'm doing, you should be able to find it in the notes as well. All right. Some of the derivations, I guess, most of the derivations, and then some. There's a whole lot more. There's a whole lot more in the notes than what I'm actually able to do live, because it would just take a lot more. It would take a few. It might take a few semesters. That'd be for any teacher with a lot of the stuff they want to do. It'd probably take them a very long time to do it because of the volume of the notes that they might have. Okay, so what about this? What are you going to say about it? Well, this thing kind of gets you there. VC vector equals VCX I hat plus VCY J hat. This is all starting to look familiar. VC vector equals negative 30, right? I hat plus negative 40 J hat meters per second. And it's a 3, 4, 5 triangle. There's a lot going on there, guys. So, I mean, it depends how strict they want to be with this. It depends how strict you want to be. I mean, it depends what you're being asked, guys. It all hinges on what you're being asked. This is true. End of the story. They want you to stop there. If they say, give it to me in component form, you just did it in component form. VC equals the magnitude of VC vector equals the square root of one of the components squared plus the sum of the squares of the components, the square root of that sum. This is a 3, 4, 5 triangle, guys. When you do that, you get VC (50 meters per second). Where is it? I guess in the game here, guys, you could say 30 over 40 is the tan of phi. So you could say, let's make sure this stuff's legible, guys. 30 divided by 40 is the tan of phi. So the tan of phi is 30 divided by 40. Is that true? Yeah, it's true. It's opposite divided by adjacent. Opposite divided by adjacent is the tan of phi. Phi is equal to the inverse tangent of that ratio, 3 over 4, 30 over 40, 0.75, whatever. Phi is going to be equal to, it should come out to 53.1. For some reason, I'm not entirely even agreeing with that, to be honest with you. Okay, I think I did something else here. In my notes, when you look at it, guys, the 53.1 would be here. I do not know what motivated me to do that, but it's neither here nor there. There it is. That's 53.1. That's this guy. That's this ratio. If you went 40 divided by 30, 1.33333, the inverse tangent of 40 divided by 30 is 53.1 degrees. That means this guy right here, the actual phi, would be 36.9. Just trying to put this thing together, guys. It's, right. 40 and then 30 and then, yeah, everything looks good. Let me just, for some reason, I'm not sure, I have no idea what I was thinking. Okay, I do know what I was thinking. I found this, 53.1. Alternate interior angles are congruent. That's also 53.1 degrees. Right here, that's 53.1. This right here is 90. So 90 plus 53.1 is 143.1. So if you're talking about theta, it's this right here at theta equals 53.1 plus 90, which is 143.1 degrees between C and A. Between C and A. A is, let me just see. Yeah, the angle between C and A, that's going to be all this. This right here is 90. This right here is actually the 53.1. This right here is 36.9. That's 53.1. So here, if you found 36.9, you'd have to add 53.1 for them to be complementary. 53.1 is here, but that's also this. So 53.1 plus 90 is the 143.1. Okay, the notes should make more sense than the near fiasco that I just did over there, but it should be pretty straightforward. The 90 and the 53.1 should give you the 143.1. Between VC vector and VA vector. And that's this. That would have been this. Uh, 50 meters per second, and this is another way to write it without using component form. I mean, VC is that big. You can write it like a vector. VC vector equals 50 meters per second at theta equals 143.1 degrees between VC vector and VA vector. You call it a vector even though that's a scalar because you gave a scalar and you gave a direction. gave a scalar and you gave a direction. Okay, it's a little on the wacky side, but I think when you look at my notes, it should be pretty straightforward. I think when I had used 40 over 30 rather than 30 over 40, the 30 over 40 would have given me the 36.9, the 30 over 40 for the inverse tangent of 30 over 40. But the 40 over 30 would be associated with that angle, and 90 plus the 53.1 gives you the 143.1. You'd get this angle, and that's an alternate interior angle congruent to that angle here. And that's when you're adding the 90 and the 53.1. Okay? Yeah, I mean, it's not too bad. Not too bad. Let us do 72. Okay, guys. All right, guys. 72 is a great problem in its own right. 72, a pendulum consists of a wooden bob of mass big M suspended by a massless rod, a rod without mass of L, length L, a bullet of mass small m, much smaller than capital M, is fired horizontally with a speed v at the bob and emerges from the bob with a speed v over 3. So it came at it, and before it hit that very massive bob, the small bullet, before it hit the very massive bob, was going at speed v. When it went right through the bob, it went from speed v to speed 1/3 v, v over 3. If the pendulum bob just barely reaches the highest point, such that it is able to swing through one complete circle, find an expression for the speed v of the bullet before the collision. Great problem. Forgive me, guys. Some of this stuff marks up a little bit more than the other stuff does. It's hard to remember here. I got some chalk, excellent chalk, and then chalk that definitely can be seen, but I don't want it seen afterwards. So it's, you want it. We'll work on it. If need be, I'll clean it. So we'll figure it out. All right. What's going on here? Well, they said what they said, guys. Let's just solve it. The bullet goes through. The bob barely gets up to the top. Let's write some data down, and let's figure out what we can say pertaining to it. So 57's done. Let's take a look at 72. So they're saying, here it is. There's a massless rod right here. There's a very large bob right here, relatively speaking, capital M. The bullet's flying through. Bullet's going really fast initially. It's not very massive. It's just small m. It's coming through at V. It emerges. It emerges not going too fast at all, but fast enough, I guess you could say. It's going 1/3 V, or V over 3. V over 3 or 1/3 V, and that's that right there. All right. So as it comes out. So we're talking about initially here, and then at the end it's going just here. Okay. So we've got this. We've got this. It hits this whole thing takes place. Not a good drawing, but this thing ends up getting up to the top, and I mean barely up to the top. It's also L up here. Well, let's use conservation of energy considerations, and let's figure out what kind of mathematics describes what we're trying to do here. So, well, I'll tell you what. We're kind of missing one thing here. This guy does have to acquire a speed. We'll call that the speed of the wooden bob. V sub W equals speed of the large M, of the wooden bob. The V and the 1/3 V pertain to the bullet. The V and the 1/3 V pertain to the bullet. But the V sub W will pertain to the large mass. They are telling us that the mass of the bullet is much, much smaller than the mass of the bob. Let's talk. We have got to make sense out of this. And the way we're going to make sense out of it is, at the end of the day, the bob acquired enough energy from the bullet to just barely climb all the way to the top of the circle. From the bottom of the circle to the top of the circle is L plus L, 2L. It climbed a height of 2L. We'll talk about that. In the meantime, the bullet, mass small m, traveling at V, collides with the stationary bob, traveling at 0. The bullet emerges, traveling at V over 3. The bob does acquire speed. It has to acquire speed. If it's going to climb to the top of the circle, it has to acquire speed. 0 times anything is 0. You got mv equals 1/3 mv. Just take v over 3 is 1/3 v. MV is 1 MV, which is the same as 3 over 3 MV. Subtract 1/3 MV on each side. You got 2/3 MV equals capital M V sub W. Divide by capital M on each side. Two MV over 3 capital M. That's VW. It's a nice little formula in its own right, all by itself. Now we can employ conservation of energy. Now we got to kind of, well, I mean, this is fine. This is okay. We're okay like this. Is it true that the bob acquires kinetic energy from the collision with the bullet? The kinetic energy that it has acquired is 1/2 mv squared. 1/2 mv squared. 1/2 capital M v sub w squared. All of that kinetic energy is going to be used to climb all the way to the top. To climb all the way to the top, which is what? Well, we just said it was L plus L. That distance right there is 2L. Climbed all the way to the top. That's it. So let's see what we got. So we're trying to find a lot of stuff is what we're trying to find, but let's see what we can find here. We are, at the end of the day, trying to figure out the speed of the bullet. We're trying to figure out the speed of the bullet, not the block. Don't worry about it. We can get out of it. Put VW as this, and then square it. VW is this. VW squared is this squared. All right. Didn't say it was going to be perfect, but let's see what we got. Square this. Don't forget, square it. What do we got? Four m squared v squared over 9 capital M squared equals m g 2L. Okay, there's a lot here. Well, we got everything here. I'll tell you what, we got the half, we got a whole bunch going on here. Okay. How about the 2? How about the 2 goes into the 4 twice? The 9 stays. 2 goes into 4 twice. You got 2 over 9. The capital M and the capital M squared cancel. You just got an M right here. So we got 9M on the bottom, and we got the other stuff going on there. So let's see what we got here. We got 9 big M on the bottom. We got 2 m squared v squared equals m g 2L. Sounds good to me. What do you say you divide by 2 on each side? Yeah, sounds good to me. What do you say you multiply by 9? What do you say you multiply by 9 capital M? Multiply by 9 capital M on each side and divide by m squared. Nine capital M on each side, multiply by 9 capital M on each side, and then divide by m squared. Okay. Now we're here. Square root both sides. Square root of v squared is v. Square root of 9 is 3. Square root of capital M squared is capital M. Square root of the product GL is square root of the product GL. Square root of small m squared is m. That should end the story. Be written a whole bunch of ways. That's it. I mean, period. I mean, you got V equals 3 capital M divided by small m. Three capital M divided by small m. That's the answer. It's the end of the day. The answer is that. V equals 3 capital M over small m times the quantity, the square root of the product, GL. Times the square root of the product, GL. V equals 3 capital M divided by small m times the square root of the product. The square root of the product, GL. Okay. That is it. Some stuff to look at. Like I said, guys, a lot of the, I believe, I've always believed, I mean, pertaining to the lectures, so much of the lectures should be contained and are contained. If we do it correctly, I think that the lectures are contained within the problems to a large degree. A lot's in there. Well, obviously, we want to know what we're doing. It's like saying, well, yeah, I'm going to send you to play a game, but I'm not going to tell you what the rules are. Why don't you learn while you're there? Well, you can sort of pick up on things and sometimes sort of not. It's good to know up front what the rules are. Then you go there, and the more you play the game, the better you are at it. So hopefully I'm giving you some background on this stuff. The book's giving you background as well. You're working hard. You're reading the book. You're looking at the notes and everything else. And again, the book is big time important as well, obviously, big time important. And then apply what you know how to do to get these answers, guys. And there we are. I appreciate your time. That was chapter 11 from the Katz book. Some more stuff to just talk about. And next time we get together, we'll look at we'll look at problems from chapters 12 and 13 as well. What order we, if I can do them all at once, or if I just go chapter 12 and then chapter 13. We'll see how that goes. Okay. Thank you so much for your time, guys. Take care.